In this video, we're going to talk about finding the volume of a solid using a method of cylindrical shells. So let's say that I have some region here and I want to find the volume of the solid that's formed by rotating this region around the y-axis. So you can sort of picture this, sort of becomes this flying saucer-shaped region, like a smushed lemon. And I'm going to find the volume, and instead of splitting this up into disks, which is what we did last time, we're going to look at an alternate method for being able to find the volume of this. And the idea is that I'm going to split this up into a bunch of shells. Well, what do I mean by a shell? I'm going to, sort of like stacking measuring cups, I'm going to fit in this a bunch of these cylindrical regions that nest inside one another. So here's one cylindrical region, and if I were to capture the next widest one, here I have another one stacked just outside of it, and I have another one stacked just outside of that one. You can see that these sort of cylinders could fill up the space. Well, what do these cylinders look like? Let's pull one out to talk about it in particular. Each one of these are cylinders that extend from the bottom of the region to the top of the region, and they have this narrow width. And we're going to take the limit as these widths get smaller and smaller and smaller. These stacking cups, the sum of the volumes are going to become a closer approximation of the volume of the solid. So what is the volume of one shell? Let's take a look. In order to find the volume of this shell, I'm going to think about what happens when I unroll the shell. So let's think about sort of slicing it and cutting it open. And when I cut it open, it forms a rectangular solid. A very narrow width, right? So I've taken this and unrolled it like a carpet, sort of, and it's going to be very narrow in width. And this width is going to be given by the width of each of these shells. And notice that the width of the shell in this case is going to be a dx measurement, a delta x. And it's a delta x measurement because I'm only taking the width from where it starts to where it stops. I'm chopping it along the x dimension, the x-axis. So for this shell, it has a dx width. You could imagine that if I were rotating it differently, and I'll show you in a second, that we could also have dy shells as well. And then this shell has some particular height. In this case, the height is given by the difference of the top function minus the bottom function. And what is the length along the base? The base length in this case is going to come from unrolling the circumference of this circle. And so if I know that this circle has radius r, the circumference of a circle is 2 pi r. So the length along the bottom is the circumference of a circle. That means that the volume of one shell, so for just one particular shell, the volume is going to be the base, which is 2 pi r, which we found by the circumference of the circle, times the height, I'm just leaving that as h, times the width of each shell, and the width in this case is going to be delta x. So if I want to find the volume of the entire region, it's going to be the summation from where my delta x's start to where they stop. And we have to be a little careful of that. We'll talk about that. Let's do that in some detail. Dx. Sorry, the delta x becomes a dx as I take a limit. So in this case, you would think that your x values might go all the way from this negative value all the way up to this positive value, right? Because that's where my x's start and where my x's stop, and that is not correct. And these shells, that would be double counting each of the shells, because the shell has this left side over here and this right side over there, and really we want to count each shell once. So for my bounds, in order to count each shell once, I need to make sure that the summation just goes from the midpoint of the figure outwards to the end. So in this example, the middle of the figure is here at 0, and then the outer edge is out here at a value of b. So in order to count each shell once, I'm summing up where do my, instead of like where is the left bound and the right bound, I'm thinking where is the center of the figure, and I'm going to sum up until I get to the edge of the figure. I'll label that. So this is the center, and this is the outer edge. That's a lot of theory, but if you really understand this theory, you don't have to memorize any formulas, and you'll be able to solve all of these problems by drawing pictures. It's important to draw pictures to be able to understand what's going on in these problems. Let's start by looking at an example. So suppose I want to rotate this region around the y-axis and find the volume of that region. So this is the upper curve here is the curve y equals x squared. And I want to find it rotating, we're going to take the region where x starts at 0 and x extends to 3. And I'm going to take this and rotate it about the y-axis. So, I'm finding the volume of the bottom piece. So I'm sort of taking the cylinder and hollowing out the cup. I don't want the top parabola cup part. I only want this base part. Sort of has a circular base. So in order to find this volume, let's draw an example of what one shell is going to look like. I'll use this green pen and see that one shell is going to go from top to bottom. It goes around in a circle, and it has some width. And again, this width in this case is a dx width. So that's my visual image of one of these shells. And as my x values get bigger, and of course it sort of extends backwards in a three-dimensional way also. So let's find the volume of one shell. Thankfully, we already have a lot of the work done for us. We know that the volume of this shell is going to be 2 pi r, the circumference of the shell, times the height of the shell, times delta x, the width. And that's a delta x because I'm chopping it up along the x-axis. So in order to actually set up our integral, we need to be able to find out what r is and what h is in this specific situation. In this situation, the radius of this shell, written in red, starts at the origin and it goes out to whatever the x value is. The radius is measured along the x-axis, and depending upon what my x value is, that's going to give me a different radius value. So the volume is going to be pi r x times the height. How tall is this function? If I know that the radius is an x value, the height is going to be how tall it is, and it's going to be where it hits this upper curve. So that's determined by the function, and in this case the function is y equals x squared, so the height is x squared, delta x. We're ready to integrate. This is the integral of 2 pi r, and the radius is an x value, times the height of the shell, which is the height of the function x squared, dx. The one missing piece we have is How much are we summing? We're summing the x's as they go from the middle of the figure out to the edge, because that's counting the total number of shells. We don't want to double count the shells. So our x values from the center of the figure out to the outermost edge go from 0 to 3. And we're ready to integrate. Our integral is, I can pull the 2 pi out front because that's just a constant. This is the integral from 0 to 3 of x cubed dx. So this is 2 pi x, the integral of x cubed is 1/4 x squared, or x to the 4th, sorry. Raising the power and then multiplying by the reciprocal. I'm going to evaluate that as x goes from 0 to 3. So I end up with 2 pi times 1/4 of 3 to the 4th is 3 times 3 is 9 is 81. And if I plug 0, the lower bound, I notice that I just get 0. So maybe I'll even write that minus 0. So this is equal to 81 over 2 pi. And as an exercise, it would be a good idea to pause the video and see if you would compute this using disks as well. If we did it using the disk method, we would have to be sure to take into account the fact that we have an inner radius that we're subtracting out and an outer radius along the outside. So this is where shells get tricky. Our previous example, we had them rotating about the y-axis, but we could also rotate them about the x-axis or about lines. And so I'm going to do an example now where we're rotating it not about an axis, but we're going to rotate it about the line y equals -2. And let's look at this region. This region is the region y equals the cube root of x, the line x equals 0, so that's the x, or the y-axis is where x equals 0. The line y equals 1, that's this line up here. Maybe I'll scale it up a little bit. This is the line y equals 1.